So previously we were able to find the generating function for this series on the left, where we are considering only zeta of even positive integers. So we found the generating function to be 1 minus pi times x times the cotangent of pi x, all divided by 2. And now we may wonder what happens if we include zeta of odd positive integers from zeta of 3, zeta of 5, and so on. And so we are going to try to obtain a generating function and see what happens. So when we expand zeta of 2, zeta of 3, zeta of 4, and so on, as we did previously, so we find this double sum for our expression, which we can, of course, invert to obtain the following infinite series of infinite geometric progressions, each of which can be summed until we arrive at this expression here. And then we can divide both sides by x to find that x times zeta of 2 plus x squared times zeta of 3 and so on equals this expression here, for which each term can be decomposed as follows. And we have arrived at this infinite series, and we don't really see how we can move further forward with this. However, if we consider the gamma function, and in particular the Weierstrass product, which is something that we will see later in a playlist on the gamma function, we see that we can take logarithms on both sides so that this infinite product becomes an infinite sum. And then we can differentiate both sides, and we get the logarithmic derivative of gamma on the left, and this expression on the right, which includes this sum here, which is familiar to what we got previously, up to changing x into minus x. And when we do this, that is changing x into minus x and rearranging, we find this expression for the series that we considered initially, up to dividing by x. And we can make some further manipulations, like rechanging the x into a minus x and multiplying both sides by minus 1 to arrive at this expression. And there's an interesting thing that we can do with this. We can integrate from x equals 0 to x equals 1. And when we do this, the left side becomes a half times zeta of 2 minus a third times zeta of 3 plus a fourth times zeta of 4 and so on. So we get this interesting alternating series, while the left-hand side requires us to evaluate this integral from 0 to 1. And when x equals 1, this is easy to evaluate. This is just log of 1 plus log of gamma of 1, which is also log of 1, and so these two terms are just 0. But we also have to evaluate the limit of log of x gamma of x as x goes to 0. And if we again consider our product and multiply by x after having taken reciprocals, we find that as x goes to 0, this expression goes to 1. So this product is just equal to 1 when x equals 0, which means that the limit as x goes to 0 of the logarithm becomes log of 1, which is 0, so that this series here is simply equal to gamma, the Euler-Mascheroni constant.